What's that?
We can talk after, yeah. So this the second rule is this one, right? And the third rule, the third law, right? Let me just make sure that everything's good. Okay, good. So the third law, it's this one, a to the m powered, and then to the nth power. This is different from the first law because this one just has one main base, where the first one there has two separate bases, but of course they're like bases, right? And this one, what would the third law be? So this will be a to the n times m times n, right? Or n times m, it doesn't matter, right? And then we have this one as well, number 4. If you have a times b to the n powered, this will be equal to a to the n times b to the nth. This only works for multiplication, and it can also work for division, like this. Like this. A divided by b to the nth powered. What is this going to equal to? A to the nth divided by b to the nth. And so what if you had a this one 6, right? Can you do this? Say a plus b to the nth powered. Is this equal to a to the nth plus b to the nth? Is that a law?
Yeah.
It's not a law. It's not. So usually students, that will be a big mistake. To do this, you need to have an expansion to expand. If n is 2, you will do what we call a distribution, right? And you guys learned the FOIL methods, right? And so on. Yeah. But for some reason here we don't like the word FOIL. Yeah. It's like we try to avoid it. So this is not a valid law. And so he never made it there. So number 6 right now, we have to come up with a newer, and the way that we can do this is what will happen if we have a negative exponent, like say for example a to the negative n, right? What is this equal to? 1 over a to the positive nth, like this. And what will happen if you had like number 7, like let's generalize this with if you had 1 divided by a to the negative nth, like this. If you had a negative exponent, you bring this up as a to the positive n, like this, right? And we can put them together like this. What will happen if you have a to the negative nth on top and b to the negative m on the bottom? Well, the a to the negative nth will be brought down, right, as a to the positive nth, and the b to the negative m on the bottom now will be brought up as b to the positive m, like this. And we can even play a little bit more about them. But these are the main laws that we will follow through. And let's do a few examples for this one before we write a little more. So how can you simplify, right? Simplify. Say 2a to the 4th powered, b to the 3rd powered, times 3a b to the 2nd powered. So we're multiplying this out, right? What is this going to equal to?
6.
So the 2 and 3 multiply to give you
6 a to the power of 5 times b to the power of 5.
So that's good, right? And this is as simple as we can write this out. You don't want any negative exponents. If you did have any negative exponents, we will convert them into positive exponents. Here's another example, right? Say I want to simplify. Say I have x y to the negative 4 divided by 2 x to the 4th powered y to the negative 2, like this. So say we have to simplify this out. Maybe all the negative exponents can be turned into positive exponents, right? Maybe there are different ways to do this. There's a famous phrase that I like to use. It's there's more than one way to skin a cat. But it's supposed to be a goat, but we changed it to a cat now. Yeah. So we have x right? The y to the negative 2 on the bottom, we can write this on top as y to the positive 2. The 2 on the bottom it remains as 2. We have x to the 4 on the bottom, and we can bring the y to the negative 4 that is on top, on the bottom, as y to the positive 4. And I put a little dot just to emphasize that there is multiplication going on in all of this, right? So now let's see. The 2, we're going to leave it there as it is. What will happen to x divided by x to the 4th?
X to the 3rd on the bottom.
We can apply the rule number 2. If we apply rule number 2, we are going to get x to the 1, right, like this, right? This is x to the 1 minus 4, like this. But that will be on top. Every time you apply this rule, it will be on top, and you will realize that you get x to the negative 3, and you will bring it down. Or if you realize this faster, then you don't have to go through all of these ordeals, right? So what about y? You do the same thing, and you're going to get y to the
Negative 2.
Yeah, so 2 minus 4, which is negative 2. So these just leaves you with this, x to the negative 3 times y to the negative 2 divided by 2, and then you turn all the negative exponents back to positive. So you're going to have 2 on the bottom, x to the 3rd, and then y to the positive 2. And what's on top then?
1.
Yeah, just a 1, just a number 1. And there is nothing else we can do for this problem. So this is in simplest form, as simple as we can write it. Let me give you a little story. I think you'll be you will find that interesting. Say for example, say you have a person over here. Let's just draw this person like this. And this person wants to send a private message, to his friend on the other side of the world, like this. And except that in between them, there's a people, of course, right? That can have access to. This is supposed to be a little building, okay? And you want to send a message to your friend, but you want to encode the message so that nobody else can understand what the message is. The problem with doing this is that they can intercept this, and you cannot send the codes to your friend because they will intercept the codes, right? So what we do is imagine this, right? And imagine that every letter in the alphabet is renamed as a number, right? Like A, for example, can be labeled as 10, B as 11th, right? C as 12, and so on and so on. So you end up with 26.
Computer science, Mr.
Yeah, but I'm just trying to tell you why would these probably be important, right? And maybe you don't want to hear it, it's fine. Yeah. But say for example you rename every single letter in the alphabet as a two-digit number, like 10, 11, 12, and so on, right? And then you end up with 26 different numbers, two-digit numbers. And say for example, let's just follow through what will happen to a number, right? And I'm going to choose a number like 3, for example. And what you decide to do is you want to send the message 3 to your friend, but you don't want the people in between them to know what this number is. So what you do is you code it, like raising it to a power, for example. So what you send is not the number 3. You raise this to a power. Say for example, you decide to raise this to the 4th power, like this. So what are you sending to your friend? You're not sending 3. You're sending 3 to the 4th power, which happens to be 81, right? So say your friend has 81 in it, and now your friend doesn't understand what the message is. He doesn't understand that you sent 3 in the first place. But what your friend does is he decides to send you back a message coded as well with his own code. So for example, instead of sending you back 81, he will send you back 81 raised to his own power. Right? Say for example, his power is 5. Right? So what is he sending you back to you?
81.
Yeah, 81 to the 5th power. Whatever that number is, right? Maybe you can figure it out. Right? It's fine. So 81 to the 5th power. And you see this huge number in the screen, and you have no idea what his code is. You don't know but you know what your security code is, right? You know that from the very beginning, the message was 3, and you raise this to the 4th power. This is your little code. Can you undo that code? Yeah. So what you do is you will raise all of these to the opposite, to the inverse of your power, which will be raising it to the 1/4, for example. That's the opposite of what you did. So what you decide to do now here is grab 81 to the 5th power, and you decide to raise this to the
-4.
1/4. Yeah, positive 1/4. And what do you think this will do?
Put it back with the.
Yeah, so we can write it as 81 to the 1/4, and then to the 1/5, right? To the 5th power. But what is 81 to the 1/4?
3.
Yeah, that's just 3. So you're not sending 3, you're sending 3 to the 5th power. And so when your friend gets the message, he will get 3 to the 5th power, but he knew what that power, how to undo that. He knows that he coded it, or his security code is 5. He can undo that, and you'll get back the original message. So the last thing that he has to do is just have 3 to the 5th raised to the 1/5, and what you will get back is the original message that you started with. And all the government sees is a different message, not the original message ever.
Can you repeat what happened after you raised it to the internet?
Let me just tell you in a different way, right? So suppose that you have a message, right? Like a letter, right? Like a letter here. And what you decide, let's make this bigger. And what you decide to do is not send this like this. What you decide to do is you put a lock on it like this. You put a lock on it, a lock that you only you have the key to it, right? And what you do is you send this to your friend, and your friend gets the message, but with a lock on it. Basically, he cannot understand what the message is. He all he sees is a message with a lock on it. And what he decides to do is he is smart enough to send it back, but when he sends it back with his own lock. This is the lock that you put, and what he does is he decides to send you back the message with his own locker. And so what do you do? What you get here, let me just do this. What you get here will be the message with your lock and now his lock as well, right? Like this. And now what do you do? Well, you have your own key. You put the lock, the green lock to begin with, so you can unlock it and send it back to him. So when you do that, you take your lock out, and what are you going to send to him or to her, right? Yeah, the message with his own lock, and you send it back to him or her, right? And now does he or she have the key for that?
Yeah.
Mm-hmm. And then that will so you have a message, you code it with your own code, send it to your friend. Your friend, what he does, it codes it again, sends it back to you. So he has 2 codes. You undo your code. So if you raise it to the 4th power, what will be the undoing that? Raising it to the 1/4 power. So that's what we did over there. To undo your 4th power, you will raise it to the 1. Of course, this is not 2-digit numbers. Some of these are big numbers, and you can see that computers have no issues with big numbers whatsoever, right? So it's the capacity of a computer can say how difficult it will be to decode these things, right? Back then in the Roman period, for example, they used to have these rings, decoding rings, they used to call them, and the rings had 2 layers, and what it does is every letter that they had, right, it will be paired up with a different letter on it. So at the very bottom of it, they will have a key that will tell you pair this letter with that, pair that letter with that, and that's it. That was the entire key. So the two people had these rings, the general and the person sending the message, right? So the person coding this message was not difficulty for them to code it, and they can easily change that by rotating the rings around. And so when they send the code, they will just look at the key, pair them up, and translate every single letter as it is. And it was a secure way to do it. It seems simple enough, but that's already complicated enough. It doesn't have to be in order A, B, C. It could be A, D, G, and in you can easily change the rings around, and that just creates very, very big difficulty of it. But in mathematics, it's fascinating how you can, giving enough time, you can decode anything. But the problem is that you don't have enough time for this problem solving, especially back then, right? Yeah, and everything had to be done by hand, which is more tedious now. Yeah, but anyway, so just something to be wary about, that maybe you will see something like this in your major, and you have an idea of how useful these exponents that we're using are. So, and also the next thing that we want to do is talk a little bit about what do we mean by raising it to an integer, right? What if you are not raising a base to an integer? What if you're raising a base to a non-integer? For example, can you do this right here? What will be the meaning of let's put this, what if we raise a base number to a non-integer power? Yeah. For example, say we have for example, what do you think will be this 8 to the 1/3? What is 8 to the 1/3 going to be?
Cube root of 8.
And so we have a way to express this. So now radicals will be another way to express this. Yeah.
The answer is 2, Mr.
Mm-hmm. But you guys agree that you can write it like this?
Yep.
As a cube root of 8, and this is nothing more than
2.
Yeah, 2. And the reason why is because 2 times 2 times 2 will give you 8. So what does 8 back to 2 is undoing the power 3 to 1/3, right? Just like we were talking about. So we're gonna describe the cube root of, right? The cube. So the nth root. So this is the definition that we will definition. We say the nth root, right? The nth root of a number like this, nth root of a. How will you describe this? This is nothing more as a to the
1 over.
Yeah, 1 over nth, and say this equals to some number b. This is equivalent to saying b raised to some power equals to a. What will that power of b equal to? What would the power of b be?
Square root of a.
Nth, just nth. Just nth. So if b raised to the nth power equals to a, then the nth root of a equals b. So, for example, say I give you this guy right here on the left side. What will happen if you raise the left side to the nth power? What will you get?
A to the n.
A to the 1 over nth to the nth power. So the 1 over n and the nth power will just give you 1. And what would you get on the right side? B to the nth power. And that's what we get here. Yeah. So these are equivalent. We can write this as b to the nth equals a, or you can write the same exact thing as b equals to a to the 1 over nth. And how do you go from left to right? Again, you can think about this as raising this a to the 1 over nth to the nth power will be b to the nth power, and that will give you that over there. But that's how we define the nth root. Is if you want to take the nth root of a, you can write this as a to the 1 over nth, and say that gives you a number b. It is because b to the nth will give you back a, right? So here are some examples, right? Some examples. What will be, say, 27th to the 1/3? So this is nothing more than the cube root of 27th, and this will give you 3. And now, what will you get if you do this? 27th, negative 27 to the 1/3. This is nothing more than the cube root of Mm-hmm. Negative 20. Can you take the cube root of negative 27?
Yeah.
I mean, yeah.
Yes.
It's integer, yeah.
No, it's a real number.
I.
Mm-mm.
No, it's integer.
It's just negative 3.
It's just negative 3.
This is negative. Why? Because
It's
this is equivalent to saying negative 3 to the third power. What is that going to be?
negative 27.
Yeah. So how, if you take the cube root on both sides, right? You see that the cube root of negative 27 will give you negative 3. So you can take the cube root of a negative number, but you cannot take the square root of a negative number. That will leave the real number alone. It will go to the complex number. Right? But so this is fine, right? This is a real value. And what about this one over here? Here's another example. What would you get if you do 4 to the 3 over 2?
Cube root squared.
Uh-huh.
40 squared.
So
It's the square
gonna
root
be-
of cube, so it's 8.
So you can think about it two different ways. Number one, you can think about it as 4 raised to the third and then raise this to the 1/2. Or someone else might say, hey, why don't you do the 1/2 first, right? So let me do it like this. 4 to the 1/2 and then raise this to the third power. So let's do the first one, right, first. What is 4 to the third going to give you? 4 times 4 is 16. 16 times 4 is 64. So this is 64 to the 1/2. And this is nothing more than the square root of.
64.
And this, when we talk about the square root of a number, we don't put a 2 over here by default. But if you put a 2 there, nothing is wrong with that. It's just that we just choose not to. So what is the square root of 64? 8. So these will just be 8. And what about this one over here? 4 to the 1. This is nothing more than the square root of 4, right? To the third power, and the square root of 4 is?
2.
Yeah, this is nothing more than 2. 2 to the third power, give you 8. They have to agree, regardless of how you do it. They have to agree. So whoever is defining this had to be thought. And there were a lot of mistakes on how we define things. Like I told you yesterday, when we defined how the rules for division works, there were a couple of stumps, and we had to correct them, that the inconsistencies. Question?
How are you able to make a fact?
So is it the first one or the second one? Both? Yeah. So do you agree with me that by the rules that we explained, that we said, what will happen? You have a base 4 raised to the n power and then to the n power. What will you do with this power? You will multiply them. 3 is nothing more than 3 over 1. So you have 3 over 1 times 1 over 2. How do you multiply these out? When you do multiply them out, what will you get? That's exactly that. Yeah. So you can split them up into that, yeah. So you can do it like this, or you can do it like that, and these will be agreeable on those terms. And then here's in a very nice way, right? I will try to see if let's write some laws, right, or rules, right? Say law, properties of nth roots. Number one, the first property will be, say you're taking the nth root, right? The nth root of the product of two numbers, a times b. This is nothing more than the nth root of times the nth root of b, like this, the nth root of a times the nth root of b. But you have to be careful here, because sometimes it doesn't, whenever it makes sense, right? Because say for example, n is equal to 2, so you're taking the square root of, say, -4 times -4, right? And then the square root of -4 is very complex, right? And the square root of -4. But when you multiply them out, you usually back that. So you have to make sure that you're using the easiest one, right? Not the hardest one. But it's fine. It's fine that it gives you complex. So complex can give you a real number and so on. So, but that's one of the rules. Number two, say you're taking the nth root of number a divided by b. This is nothing more than the nth root of a divided by the nth root of b. That's perfectly fine. Number three, can you do this? The nth root of a plus b to be equal to the nth root of a plus the nth root of b. Can you do this?
No.
Yeah, you can't do that. That's not going to be a rule. So we got to cross this out. So if you have the nth root of the sum, you cannot just add the nth root of a plus the nth root of b. Then number 3. Say here you have the nth root of the nth root of a. Say you have this right here. This is nothing more than, right, the m
To the n.
m times nth root of a, like that. Right? You just keep accumulating them. And here is the last one, number 4. And this is interesting because this one will depend a little. So what will be the nth root of a to the nth powered? What is this guy going to be? Well, this one will depend because you might say, hey, isn't this nothing more than a to the nth to the 1 over nth powered? Isn't that? Right, we can write it like this, right? What do you think this is going to equal to?
So it can be the n.
Well,
They cancel. Just a.
You are expecting these to cancel out and you get back a, but it doesn't happen like this. It's not as that. We become conditional. Let me just explain that, right? This is equal to, one thing could be is a, and the second thing that it can be is the absolute value of a. I will explain that in a second, right? So the first one, when is the first one? The first one will be if n happens to be odd. Right, and the second one will happen if n happens to be even. So think about it like this as an example, right? What will be the square root of? Again, this is the square root, right, of negative 2 to the second power, like this. So this guy here is going to be
Negative 2.
Well, negative 2 squared will give you positive.
Positive 4.
Yeah. So this guy here will be the square root of positive 4, and the square root of positive 4 will give you 2, which is the absolute value of negative 2.
Yeah.
Yeah. So we how can you get negative 2 from a square root? You can't. Yeah. And then what about this as another example? What will be the square root, right? The cube root. Let's put the cube root, right, of negative 4 to the third power, like this. What do you think this is going to equal to? Now it's an odd. We're considering the odd case, right? Yeah, this will just be
Negative.
yeah. So is the cube root of negative 4 to the third power is negative 64, and the cube root of negative 64 is just going to be negative 4. So it's just negative 4 to begin with at the very beginning. Yeah, that's what this is telling you right here. That if n is even, then you cannot get out the negative that you had there. You have to be the absolute value of that. If n is odd, then it will be whatever number it was in the very beginning. So if it was negative, it will be negative, right? That's fine. So just know that. And then here's another rule. Let's add this one, number 5. Say you're doing a to the power m over nth. You can think about it like this as a to the m and then raised to the 1 over nth, or you may think about this as a to the 1 over nth, then raise this to the m powered, or you may even write it in different forms. Like for example, you can also write it like this, like the nth root of a, all of these to the m powered, like this, or you can write it like this one right here. This is nothing more than the nth root of a to the m. There's so many ways that you can write what a to the m over n is, right? But hopefully this gives you that a feeling that you can do all of this. So let's do a little simplification, right? Simplify the following. So here's some examples for simplify. Simplify. Say the square root of 32. 32 is not a perfect square. So if you are familiar with perfect squares, right? Perfect squares. What are these perfect squares? So if you start off from 0, then the next one will be 1, then the next one will be 4, then the next one will be 9, then 25 and
49,
yeah, 49, 64, and then 81, and so on, right? The 100, right? 121, and then 144, 169, 196, and so on, right? But just it's I would say to be sure, just we usually are capable of remembering the next few numbers until 20 squared, for example, right? That's after 20 squared, we don't have a calculator, so we wouldn't test you after that, right? So what is 20 squared? 20 times 20 is
400.
yeah. So the square root of 400. After that, the main important numbers after that will be like 25 squared, 625, for example. Like yeah. But in any of the cases, which of these numbers, right? Which is the largest perfect square that goes into 32? 16. You know that 4 goes into 32, but you don't want to use just any perfect square. You want to use a larger one. There's nothing wrong with using 4, but you will not be done in one step. You'll be take several steps. And so we are going to choose 16. 16 times what gives you 32? 2. So we're going to break this up into the square root of 16th times the square root of 2. That's what's going to make up 32. But what is the square root of 16th? 4. So this will be nothing more than 4 the square root of 2. 4 square root of 2. And here's another example. Right? Say we want to simplify. Say the square root of let's choose 50. What is the square root of 50? Well, the largest perfect square that goes into 50 will be, so this will be the square root of 25 times the square root of 2. And then the square root of 25 will be, yeah, so this will be 5 radical 2. 5 is square root of 2. And what about this other example here? Say simplify the square root of 27th. So which is the largest perfect square that goes into 27th? 9. So it will be the square root of 9 times the square root of, yeah. And the square root of 9 is 3. So this will be 3 square root of 3. And let's add another one. So here's an example of, so simplify. Say we want to simplify the square root of 32 plus the square root of, say, 200. So the square root of 32, we already know that what goes into 32 is 16 times 2. But what goes into 200? The square root of 100 times?
2.
Yeah, the square root of, yeah, square root of 2. And that's the largest perfect square that goes into 200. 25 goes into 200, but you want to use the largest possible perfect square that goes into 200. And then this becomes 4 square root of 2 plus the square root of 100 is 10 square root of 2. So can we add this up here?
Yeah.
This will give you 14 square root of 2, and that will be nice, right? We're trying to simplify it, or trying to get used to what do we mean by in simplest form. You get to a form that you can't simplify anymore, like the square root of 2 here. You cannot go beyond that. That will be as simple as we can. The next thing that we want to be familiar with is rationalizing the denominator. So rationalizing the denominator or numerator. If you're familiar with the term derivative, for example, if you're familiar with that, this is when we are use this concept of the rationalizing the denominator and numerator when we're trying to find the derivative of something by what we call a limit definition. But for now, suppose that I give you this example here. Say I have 3 divided by the square root of 6. You see how we have a radical on the denominator? Just like having a negative exponent, having a radical on the denominator is not what we want. Is there any way that we can get rid of that radical on the denominator?
Multiply on both sides.
By?
By square root of 6.
The square root of 6 over square root of 6, and top and bottom, right? And so on the top we're going to have 3 square root of 6, and on the bottom we're going to have radical of 36, which is just 6. Or you can just think about this as radical 6 times radical 6, the radicals will just cancel. Yeah. So can you simplify this out a little? The 3 and the 6, right? Yeah, the 3 and the 6, you can divide them by 3 and you're going to get... Or some people want to put a 2 there, but 1 radical 6 over 2, but you don't need to put the 1 in front of it, right? This is perfectly fine. How will you rationalize this right here? So here's another example. How will you rationalize, say, 2 divided by the cube root of 5? How will you rationalize that? How do you get rid of the cube root of 5 on the bottom? So that
Same way you did
the problem, if you do that, you won't get rid of it. You're just going to get the cube root of 5 times the cube root of 5.
You raise it to the third power?
It's something like that. Yeah.
So we change it into an exponential form, like the denominator.
Okay, let's change it to exponential form. So 2 divided by 5 to the...
1/3.
Now...
So now we bring it up. So it's going to be like 2 multiplied by 5 to the negative power 3.
Sure, but then you have a negative exponent.
Right there.
Right?
Do the whole thing. Just leave it
Yeah,
like that.
Yeah, like do the whole thing,
Raise
put
everything
cubic
to
root
the-
down. Like I can't explain it to you unless I show it to you.
So we should multiply by something, right?
Raise everything to the third power?
Well, we've raised everything to the third power, you change the quantity, you get a new quantity raised to the third power, right? So you want to multiply this by 5 to what power? Let me just explain it to you this way. You want to raise this to 5 to some power, so this and this right here will give you 5 to the 1, for example.
So 3 over 1.
Not 3 over 1.
Just 3. Just 3.
So 1/3 times what here? Times what? So 1/3. So 5 to the 1/3 times 5 to the what will give you 5 to the 1. So
5
what?
to the power of 1/3.
So these are same bases, right?
Yeah.
What would you do if you have 5 to the a times 5 to the b? You end up adding the exponents, right? So you want to add these two exponents.
The
to
2/3.
2/3, yeah. So because if you multiply this 5 to the 1/3 times 5 to the 2/3, you're going to get 5 to the 1/3 plus 2/3, and that will give you 5 to the 1. Yeah. So you avoid negative exponents, and you get an expression on the bottom without a radical, right? So let's see if this works out, right?
So you
So
always want the exponents to equal to 1.
yeah. In reality, it doesn't have to be 1. 1 will be ideal because you don't have to simplify anything after that. You want a whole number, but 1 is ideal because you don't have to simplify it afterwards. So say you multiply this by 5 to the 2/3 and 5 to the 2/3, so that in reality you're not changing the quantity, because what does this whole thing on the right side simplifies to?
1.
1. So you're not changing any quantity. You're not raising it to a third power, for example. And what would you get on the bottom now? 5 to the
5 to 1.
which has no square root or a cube root in this case, right? So you will get this right here. This is nothing more than 2 times 5 to the 2/3 divided by 5. And although you might say that we can simplify the 5 to the 2/3 divided by 5, well, we choose not to do that, because if we do that, we're going to go back to where we started, right? And so this is fine. This is simpler than
Or do you multiply
yeah.
it?
So the directions over
So
here.
how is that 5 at the denominator?
Hmm?
How is that 5 at the denominator at the bottom?
Yeah, so 5 to the 1/3.
No, no, right here, right here. Yeah, yeah.
This one? How do we get the 5 on the bottom?
No, no, like why is it only 5? It should be 2/9.
No.
No, you add
5 to the
exponents.
A times 5 to the B, you add the exponents, right?
Oh yeah.
So these will be 5 to the 1/3 plus 2/3 on the, right? They add up to 1. 1/3 plus 2/3 will add up to 1.
So can you explain me again what you're doing? Like how did you get only 5?
Sure. So imagine you have this, right? 5 to the 1/3 times 5 to the 2/3. What is this going to give you? 5 to the 1/3 plus 2/3.
Okay.
Yeah, why? Because a to the m times a to the nth will give you a to the m plus n, right?
Okay, you're adding them. Then what?
Yeah, so these will just be 5 to the 3/3, which is 5 to the 1, and then just 5.
Oh, I see. 5 to the 1.
Is that okay?
Yeah.
Yeah.
Makes sense.
Yeah, that's on the bottom. Yeah. Okay.
But
So
I think you can do it the other way. Like you can square root the whole thing and you will still get the same answer.
if the problem with by raising it to any power or taking anything else, right, is that you're changing the value of the original number. You now are creating a new value on it. So you want to multiply by 1 here, so you're not changing the value of this. You're keeping that value as it is.
So you're just basically simplifying it rather than solving it.
Yeah, so the goal for this one, the instructions for this one will say rationalize the denominator.
Oh, I
You,
see.
you will only do that if you're instructed to do it. For example, if you're working in the problem, the answer comes out to be this, leave it like that. That's the answer. But if I say rationalize the denominator of your answer, then I don't want that. I want this. So just so that we only do this, right? If we're asked to rationalize this, we only do this if we are asked to rationalize our answer. Yeah. So for example, if you're working in a test problem and you get these as the answer over here, that's perfectly fine. But if the question tells you to rationalize your answer or the denominator of your answer, then you will want to give me that then, rather than the other one. Right? So it's not a big deal. The only deal that this plays a role later on will be that there are different ways to evaluate something, and one of the choices would be that if you rationalize the expression, you have a different way of writing it, and all of a sudden you can do something with that expression that before you couldn't do. But just know that this is a common thing, that to rationalize the denominator, because it allows you to do some things that you couldn't do before. Later on, we're gonna have a name for these. We're gonna call that the conjugate of it, right, of an expression. But we're gonna get a little bit more familiar with these things. So let's consider this right here. So some examples, right? Examples to see where we are right now, and then after this we are going to take a break, right? So let me put some problems out, and then I will give you the answers to these problems, right? So number 1, evaluate, say, -2 to the -3 times, and 2. I'm going to give you the answers afterwards, right? And then we can, and to see if this makes sense or not, right? So that's 5, 6.
You solved it right now?
Mm-hmm. Yeah, it's on your paper.
Man, I didn't bring my paper.
You have to be prepared, right?
Man, I thought we are just gonna take the notes.
Yeah. Okay. So on a piece of paper, right? Try to see if you can do this. I'm not collecting it; it's in your notes, right? I'm gonna give the answers after some minutes, and then after this we're gonna take a break. So I'll give you a couple of minutes, maybe 5 minutes, to see how much you get done, and after that I'm gonna start giving out the answers, right? So that you can see if you're getting the right answers. If you don't know how to do something, then hopefully you can see how it is done, and you can get something out of it. Right? Okay, 1 more minute and then we're gonna start going over it. So let's start. I will start giving out the answers, right? And if you want me to explain a little bit more about it, then I can do that. But what will be the answer for the first one here?
-1/2.
Yeah, -1/2, right? Right. If you guys have a question, just raise your hand and I can go over it, right? But again, what about the answer for the second one? 1/9. 1/9. Good. 1/9. And what about the answer for the third one?
3.
3. So when you do that, there are so many ways that you shouldn't rationalize it. You can apply the rule that you're dividing two radicals, right? This is just going to be the radical of the division. 54 over 6 is 9. The square root of 9 will become 3. So that's good. So this will be 3. And for this one, the rules for exponent, there are many ways that you can do this. But if you do this one, you're gonna get 1/2 x to the 7th, right?
Yeah.
Then times y to the 13th.
Now y cube.
Sorry, let's see. Y to the third power. Okay, there we go. That's good. Is that what you guys got? Yeah. So if you guys have a question, we can go over it, right? But again, so go over.
Can you show that one?
Sure. Number problem. So number 4, right? So let me just copy this. Ouch. There we go. Copy. Yeah. And let me do it here. So for number 4, on the bottom, right? There's many ways that you can do this, but I'm going to focus on the bottom first. So I'm going to have 8x to the -3, y to the 5th powered. On the top and the bottom, I'm going to apply this rule where I'm going to raise 4 to the 2nd power. That's going to give me 16th. I'm going to have x squared to the 2nd power. That's going to be x to the 4th. And y to the 4th, I'm going to raise it to the 2nd power. That's going to give me y to the 8th. So I'm going to have on the bottom 4 squared, which is 16th. X squared to the 2nd power, that would be x to the 4th. Y to the 4th, then to the 2nd power, that was going to give me y to the 8th power. And now I have this. Now I'm going to change the negative exponent for x into positive exponents, right? So that's going to give me 8 y to the 5th powered divided by 16 x to the 4th, x to the 3rd now, and y to the 8th. So the only thing that I did there was turn the negative exponent to positive. That's the only thing I did. Now can I simplify 8 and 16 here?
Wait, so to turn it positive, you don't have to do anything, you can just change it to...
Yeah, so if the exponent is negative on the top, you move it on the bottom, and all of a sudden it has it right here, it's here now. Yeah, so if it's negative on the bottom, you move it on the top, and it becomes positive.
Wait, so what you leave on the top and what you raise the bottom?
Yeah, so only the base to an exponent. So nothing else. You'll just x to the -3 will be moved to the bottom as x to the +3 on the bottom. Yeah, that's one of the rules that allows us to do that. And so that's the only thing that I did from here to here. So 8 and 16, you can simplify them, right? That becomes 1/2. And then x to the 4th on the bottom, x to the 3rd, that will give you x to the 7th. So far, this will give me 1/2 x to the 7th. And what happens with the y's? when you do subtract them, right? You get y to the
Third.
negative 3 on the top, right? When you apply the rule, but then you have to bring it back down. This rule is y to the 5 divided by y to the 8 will be y to the 5 minus 8, and that will give you y to the negative 3, right? And so the last thing will be I don't need the y to the negative 3 on the top. I'll put it on the bottom, and so I'll get this like that. So these will be the answer for that one. Is that okay? Yeah. Okay. And then let's just wrap things up, and then we take a break. So the square root of 75. 75 is 25 times 3. The square root of 25 is 5. So it's 5 radical 3. 5 radical 3 plus 2 times, and then square root of 48. 48 is 16 times 3. 16 is the largest perfect square that goes into it. And so you're going to have the square root of 16 as 4, and then the square root of a 3 next to it. So you end up having 5 radical 3 plus 8 radical 3, and that will give you
13 radical.
13 radical 3 in it, right? On the right side here, number 6, it says rationalize the denominator and simplify it. My suggestion for you on that one would be to simplify radical 8 first. Radical 8 can be simplified as 2 radical 2, and then 12 divided by 2 radical 2, you can simplify that as 6 over radical 2, and then you rationalize that, multiply by radical 2 of radical 2. So you're going to have something like this. You're going to have 6 over radical 2. When you simplify and rationalize the denominator for this one, you multiply by radical 2 over radical 2, and that's just going to give you
3 radical 8
3
over
the
2.
square root of 2.
3 square root of 2. Yeah, like that. So that'll be the answer for that one, right? Just that 3 radical 2. And for the last one here, I'm gonna take a few steps. This is nothing more, and this is what I'm gonna do first. First, I'm gonna turn the negative exponents in here into positive exponents. So that will be something like this: 2 b to the third divided by a to the third, a to the second power, and b to the fifth power, like this. Now what I'm gonna do is I'm gonna change the negative exponent out here to positive exponents. And that was one of the rules. That how did you do that? What we do is the bottom becomes the top, and the top becomes the bottom. That will be an application of the rules that we have there. If you remember, a to the negative n divided by b to the negative n, we switch them, both of them, the top and the bottom.
The
That's
answer
exactly
is a to the power of 10, b to the power of 4 over 4.
Yeah, but let me get there. Yeah. So that's what I'm gonna do. This negative exponent will become positive if the denominator and the numerator change, like this: a to the third, a to the second, b to the fifth, divided by 2b to the third, and now the exponent out here will become 2, positive 2. So the top became the bottom became the top. And let's skip a little bit more here. So we're gonna have, so let's distribute out the before we distribute this out, right? On the inside here, we're gonna have a to the fifth power, and then b to the second power divided by 2. So it will look like this: a to the power 5, b to the power 2, divided by 2, just 2, right? And finally, the answer here will be a to the 10th, b to the 4th divided by 4. But that will be the answer for the last one. So let's take a 20-minute break. 20-minute break, yeah. So it is now 10:36. We're gonna be here at 10:56, right? So that should give you enough time to, stretch your legs. Yeah. So if you need to see something, we can, yeah. But 20-minute break. So
That's a long break, Mr.
yeah. If 10-minute break will not be enough for you to, right? Some people didn't eat breakfast yet. Yeah. Some people. Yeah. Yeah, and it's a 3-hour session. It's a very long session. I have 4 classes to teach as well, so it's not ideal for me either. So the section that we are going to cover now will be section 1.3, and tomorrow we can give you the details of where the PDFs and the will be posted, and the quizzes, the solutions to the quizzes, the homework, the solutions to the homework, and so on, so that you can keep track of all of this. And sometimes you want to be organized, and we can show you that tomorrow. But so the section that we have now is 1.3, and These algebraic expressions. And what we're gonna do is we're gonna focus on polynomials in this section, like for example, distributing a polynomial, multiplying a monomial by a binomial, binomial by binomial, and so on. But we're also going to talk about a little bit of factoring and some factoring techniques, so that if you are weak on that, hopefully you get to review a little bit on it. And so the main focus on this one, on this section, is polynomials. So how do we define a polynomial, right? So the definition. A polynomial is nothing more than an expression in this form, right? The polynomial is an expression in the form, say, a coefficient times a variable, right, plus a second coefficient times a variable, and plus dot dot dot, and you can imagine how this is going to go, times a 2 x squared plus a 1 x plus a 0.
I think I zoomed in too much.
Is zoom okay? Well, here is perfectly fine. I don't know why there it's. Let me see if I can unplug and plug this back in. Yeah, let's check this out now. Let's see. Oh. Let me see if I can plug this up. And let's check this out now. Okay, better, yeah. Because here I have it regularly. It's like, let me know if it happens again, right? So this is how we define a polynomial. It doesn't have to go to a very, very high power. The powers for these ones are going to determine the degree of a polynomial, right? And what you notice here is that every single one of these has a variable, x, and it has a coefficient. These coefficients here are this is just a way to name those coefficients. We call this a subscript technique that we generate. Is a 0, a 1. Like, we don't want to use a, b, c, d, e, because we will run out of letters, and so we create a system like this one where we use subscripts and we never run out of letters. So it's very nice. So this is just a constant coefficient. This is the linear coefficient, the quadratic coefficient, and so on and so on and so on. Let me give you an example here. But the first thing that you notice is that these powers for x, the variable x, are always whole numbers. They're always whole numbers. And the second thing is that it never a negative whole number. We say that these powers here belong in the set of natural numbers. You remember, right? The whole number is better because we can start off with x to the 0 here. But anyway, so note, right? So note that the exponents for the variable x are in the set of whole numbers. Namely, this set right here, if you remember it from yesterday, 0, 1, 2, 3, but they're not negative. Having a negative exponent is bad. Do you have any idea what will be bad about it if you have a negative exponent? Have you ever heard of the term a vertical asymptote? That's what this will create. You can have a polynomial with any powers coming from this set, no vertical asymptotes.
Mr. The whole numbers are the same as integers, right?
No. When integers will have negative. We defined that yesterday, right? The set of integers will have negative 1, -2, -3, -4, and so on.
So whole numbers doesn't include any negative number.
No, we established that yesterday, and this is what we said yesterday. The integers was this guy here. Yeah, counting numbers, the natural numbers, whole numbers are this one. Yes. So they're not the exponents are not coming from the integers, the set of integers. This is coming from the set of whole numbers. But so you're with me that if the exponents are choosing from this set, no problem whatsoever. But all of a sudden, if you choose a negative exponent, what will happen is that all of a sudden you will have later on we can talk about this. This creates a vertical asymptote, and that's problematic for us because a vertical asymptote we classify a vertical asymptote as an infinite discontinuity. We classify that as a singularity, and these guys have no singularities. They don't have any discontinuities. That's perfectly fine. Sometimes these are called they're classified as analytic in the sense that they're smooth. But anyways, it's fine. But so we will say that here's an example, right, of a polynomial. Example. Yeah. So let's put some examples. Number 1, say I give you 2x cubed minus 50x plus 11th. Is this a polynomial? Sure. This is a polynomial. How many terms are in this polynomial? Terms. Terms are three terms. And what would be the degree of this polynomial? Yeah, the degree will be not the number of terms. It will be the highest exponent that we see, right? The highest exponent in this case is 3. And so you can see that it's a polynomial with 3 terms, and the degree for this one will be 3. I can say a little bit more about this one, but for now this is good enough. That's that. Here's another example. Number 2. What if I give you, say, 5 x to the 4? Let me put x to the 4 plus 4. Like this. What about this one? Is this a polynomial? And how many terms do we have here? 2. And the degree for this one will be 4. But we get the idea, right? And what will be the coefficient of the highest degree? The coefficient for this one will just be 1. The coefficient of x to the 4 is just 1. And so, what about this example here, number 3? What if you just have x like this? Is this a polynomial?
No.
Yeah, it is. The exponent for this one is 1, so it's perfectly fine. So what will be the number of terms in this polynomial? 1. And then the degree for this one will be 1. So this is perfectly fine. Like if you put x squared, for example, that will still be a polynomial. What about this one over here, 4? If you just put a number like 50, can that be considered a polynomial? And the answer is yes. It's a polynomial. The degree for this one, right? So the terms for this one, the terms here is 1, and the degree for this one will be 0, exactly. And 0 is okay. The exponent could be 0.
Okay, sure, yeah.
Yeah, but if I put something like this, for example, like these are examples, right? Let's put this in the non-examples, right? This is non-examples, meaning that these are not polynomials, right? Number 1, say for example, if I put x to the -1, also as 1 over x, you see that's not a polynomial. You have an exponent of -1 is not an exponent in the in one of these exponents. Number 2, so that's not a polynomial. Number 2, say I give you 2 to 2. Let me write it like this as the square root of x. That's better. This is not a polynomial. And you see, when it's not a polynomial, it has restrictions all of a sudden. What will be something that you cannot plug in for x in here?
0.
0, because then you're in trouble. So that creates a problem. This one right here, what is it that you cannot plug in? Negatives.
Yeah.
You cannot plug in negatives. You try to plug in a -1, for example, all of a sudden you leave the real world, right? And so that's not good. So you create problems if it's not a polynomial. And what about this one? And we will talk later about this ones right here. Are you guys familiar with? If you haven't seen it, it's fine. Have you seen this guy right here? Right, this is an exponential example of an exponential expression. This is not a polynomial. It creates some problems, and we can talk about that. For example, these doesn't have any vertical asymptotes, but it will have a horizontal asymptote, right? And so what about number 4 here? Probably you are a little bit familiar with that one. This is a trigonometric function. Is that a polynomial? No, and it creates some problems as well. You cannot go beyond a certain number, and you cannot go lower than a certain number. So something is, we call that boundness, is bounded between two numbers and so on, right? Hopefully you're familiar with that, and so it has an amplitude and so on. Yeah, so these are not. And I'm going to put another example, and hopefully you have seen this as well, or not. Have you seen this? The natural log is a log under a special base, right? Yeah, but this one is not. This one has a lot of problems, and well, it's also nice. But these are not examples of non-polynomials. And we can talk more about this, but this is fine, right? So when we define a polynomial, we can get familiar with the how many terms there are, what the degree is, and so on. But how do we add two polynomials? Adding, subtracting, multiplying, and dividing. Polynomials. The last one, I'm going to put this with a red line right here. Because when we divide polynomials, all of a sudden, these will be called rational expressions. Rational expressions. And the section for this one will be in 1.4, the next section, 1.4. So what we're going to do now is just going to focus a little bit on these three things: adding, subtracting, multiplying, and then we're going to talk about factoring as well, right? Undoing the multiplication part of it. So here are some examples, right? Examples. So say I want you to add and simplify these two polynomials. Say I have x to the third minus 6x squared plus 2x plus 4, and you're adding this to x to the third plus 5x squared minus 7x. How do you add two polynomials? You
Add the exponents.
You look at the like terms, right? Yeah. So x to the third here and x to the third, these are like terms, right?
2x.
Yeah. So that will make 1x to the third plus 1x to the third. That will give you 2x to the third. X to the second power here and x to the second power, these are like terms as well. Negative 6x squared plus 5x squared, that will give you negative 1 or negative x squared. And 2x plus negative 7x, negative 5x, and the 4 here doesn't have any like term to add this up with. But at least we get an idea that this guy here will be 2x to the third minus 1x squared, or just x squared, minus 5x, and then plus 4. But these will be the answer. That's how we will leave it as. There's nothing else we can do about that. That's it. Adding two polynomials will give you another polynomial, right? And so, what about if I ask you to simplify this, right? Subtract and simplify. And simplify. Say I want you to subtract x to the third minus 6x squared plus 2x plus 4 minus, and then x to the third plus 5x squared minus 7x. Just what we have here. When we're subtracting,
So let's say the second polynomial had different exponents than the first, you would just leave them the same, right?
Combine them.
Yeah, so we will combine. So for example, if here has an x squared, right, and this one doesn't have an x squared whatsoever, so you leave that as negative 6x squared, right? You combine anything that has the same exponent, right?
Right.
If there are no matching exponents, then
So like if you know how there's a 5x squared in the second polynomial?
Mhm.
Let's say the negative 6x still has a squared,
Mhm.
but the 5x has a like 4. You would just bring that down, right?
yeah. We can give more examples if you want to, but it's just we match up the like terms and we add them up just like we do, yeah. And the idea for that one is that these will be very important for physics and chemistry. That if you're adding squares, meter squares, you cannot add an expression with meter squared with an expression with meter cubed, for example. That would not be something that is we can't do that. And so we want to be careful on matching these units in sciences, right? Like physics, for example. So exponents will be a way to tell us what units can be added and what units cannot be added and so on. Of course, units can be converted, right? But anyway, for the second one, my suggestion for you when you're subtracting polynomials is to distribute the negative, right? And then some people do it mentally, and that's fine, right? But if you can do something like this: x cubed minus 6 squared plus 2x plus 4 minus x cubed minus 5x squared plus 7x. So do you see what we did there? We just distribute out the negative sign like this, and we get this. By doing that, now some people call this clearing out the parentheses, right? Whenever you have to, if there's a 2 here, you will distribute out the 2, but there's a minus, so we distribute it out. So now that we have this, now we do the same thing that we did before. X cubed minus x cubed here, they will just cancel out, right? They're gone. So what do we have next? So negative 6x squared minus 5x squared will give you negative 11 x squared. And we talked about that yesterday, that if they have the same sign, right, like negative 6 and negative 5, you can just factor out the negative and add the numbers 6 and 5. That will give you 11 and keep the negative sign there. What about the next one? 2x plus 7x will give you 9x, and you still have plus 4 there. And this will be the answer that we get for this example here. And what about multiplication, right? Here's an example for multiplication, right? Example. Multiply and simplify. And simplify. Say I have 2x squared plus 1, and I'm multiplying this by 3x minus 5. Say I'm multiplying this out. How do we do this? You remembered a technique that we call distribution, right? And the idea will be, let's distribute things one at a time, right? So focus on the 2x squared. When we multiply this out with that guy, what is that going to give us? 2 times 3 will give you 6. X to the third. Yeah, that's what we get when we do this. What about distributing out 2x squared with a negative 5? What is that going to give you? Mm-hmm. So we're distributing at the same time. We're paying attention to what happens with exponents, right? 2x squared times 3x. We multiply 2 times 3. That'll give you 6. And x squared times x. Right? We add the exponents based on our exponent rules. So everything is connecting and trying to keep track of what we have done in the past. What about the next term on the left side, like the 1 here? Yeah.
Just leave it. You can copy that one.
Yeah. So we distribute out the 1 times 3x, and that's going to give us 3x, and we have one more, right?
Minus 5.
Yeah, the 1 times negative 5. That's going to give us negative 5. Do we have any like terms to combine? No. If we did, we would, but we don't, so we won't, right? So these will be the answer that we get, and so that's fine. Let's do another example, and in the next example, we do have something to combine, right? So just let's keep that in mind. So here's another example. What would you get if I asked you to multiply and simplify say I have 2x plus 4 times 3x minus 1. So let's do the same thing that we did, but now let's do this a little bit faster. So 2x times 3x, that will give me
6x squared.
6x squared. The 2x minus times negative 1 will give me
Negative 2x.
negative 2x, and then the 4 times 3x will give me
12x.
and then the 4 times negative 1 will give me.
Minus 4.
And now we have something else that we didn't have before. We have to consider the like terms, right? And so that's going to be 6x squared.
Plus 10x.
Mm-hmm. There we go, minus 4. And that's it. Notice that here in the last expression, you see how you have 6x squared plus 10x minus 4. They all have 6, 10, and 4. They all are multiples of 2. Some people, they will get used to factoring things out. That what they want to do is factor it out. Don't do it. If the question doesn't ask you to factor anything out, don't. It is fine, right? You don't. That's just going beyond what they ask. If they wanted to factor it out, they will tell you factor the expression out. And, yeah. So if you do it, it won't be wrong. It's just you're doing a little bit more than what they ask.
Are you gonna ask us to factor it out?
Yeah, but now let's move on to that section, right? Worrying about how do we factor things out, and so there are let's say 5 formulas that just keep them on the back of your mind, and these are distributing formulas or product formulas. And what we're going to do is we're going to use those formulas backwards to factor things out, right? So just consider this right here. See these are product formulas. These will be helpful for us to know how to factor things out. So helps for factoring. So for example, number 1 is what would you get if you have a plus b squared? A plus b squared is nothing more than a plus b times a plus b. And you know what to do now. You distribute things out. But what do you get when you distribute this out? You're going to get a squared plus 2ab plus b squared. I'm skipping steps there. I'm hoping that you're familiar with what will happen to get from the second stage to the first stage. I just helped you out a little bit there so that you don't distribute the power 2. You learned that we couldn't do that, right? This is not a squared plus b squared. It's not, right? He's going to have this extra guy in the middle, 2ab. And then we call this the sum of two the square of the sum of two numbers, right? What about number 2? What if you have a minus b squared? What if you have this? Then this is nothing more than a minus b times a minus b.
A squared, b squared.
And when you do this, when you distribute this out, you're going to have a squared minus 2ab plus b squared. But how do you get this? Again, you distribute it the way that we did this before. A times a will give you a squared. A times negative b will give you negative ab. Negative b times a will give you negative ab. And negative b times negative b will give you b squared. We combine the middle terms because they're like terms. And number 3, what will happen if you have a plus b and you multiply this by a minus b?
Just a squared, b squared.
Yeah, and with a minus in the middle, right? Yeah, so these comes out to be a squared minus b squared. Yeah, sometimes we call this formula the difference of two squares, right? A squared minus b squared. And number 4, and this is when things start to get a little bit longer. And so number 4, what will happen if you do a plus b to the third powered? So this is nothing more than a plus b squared times a plus b, right? So a plus b squared is nothing more than what we had over there, a squared plus 2ab plus b squared times a plus b. And when you start distributing this out, things get just a little bit long, but nothing bad. These it turns out to give you this: a cubed plus 3a squared b plus
3b square a
a squared ab squared plus
b cube.
b cubed. And this is a version of expanding things. And if you're a little bit familiar with Pascal's triangle, that's how we get the coefficients a 3 3 1 3 3 1, right? Like the coefficients for this one, 1 3 3 1. But anyway, so we don't need anything.
I have a question really quick. Some people say that 2 to the power of 3 as 2 to the power of 3, while other people say 2 cube.
Mm-hmm.
So which one is correct or both?
They're both wrong, both correct. It doesn't matter.
Yeah.
It's. I mean, if I think in mathematics we just try to focus on what the definitions are. But it's. I mean, if you want me to say it, a cube.
It doesn't matter, right? Both mean the same thing.
Yeah. Again, these formula is a little bit long, but you can just start distributing things out, and you simplify combined like terms, and you get in something like that. If you want to search a little bit about how we get these things, like what will happen if you do to the 4th, to the 5th, to the 6th power, you can just Google Pascal's triangle, and it tells you the method of doing this. But we're not going to need anything more than to the 3rd power. So number 5, say a minus b to the 3rd power. This is a minus b to the 2nd power times a minus b. And this is nothing more than a squared minus 2ab plus b squared. And then multiply this by a minus b. And these, all of a sudden, will give you a cubed minus 3a squared b. Right? And then plus 3ab squared minus b squared, b cubed, like this. And the way that we remember this, the way that we will use this is backwards. What if I gave you the right expression, right? What if I give you the right expression? Can you reproduce the left expression? And so we have to learn some techniques on factoring because of that. So let's see if we can do this right here. The next thing that we want to do is get a little familiar with factoring out. So the first thing, factoring. The first thing that we want to learn about factoring is what the GCF is, right? The GCF, and the GCF, we will call this as the greatest, right? Greatest common factor. Let's just put common factor like this. Common factor. So imagine I give you this example. Say I give you. I want to factor just the GCF in the expression. Say 3x squared minus 6x. Say I just want to factor out the GCF from it. Between 3 and 6, what will be the greatest common factor between 3 and 6? 3. Between x squared and x? X. So the greatest common factor here that we'll factor it out will be 3x, and we'll have x minus 2 in it. Because if we were to distribute the 3x, the GCF out, 3x times x will give me 3x squared, and then 3x times negative 2 will give me negative 6. So these will be the answer that we're seeking just for this particular problem. This is the expression, the same expression, but we factored out the GCF from it. Here's another example. And we want to impose the same instructions. We want to factor out the GCF only from it. So say I have, and let's see if this makes sense. 8 x to the 4th y squared plus 6 x cubed y cubed minus 2x y to the 4th. The same expression here. The same instructions to factor out the GCF from this expression.
2x.
Yeah.
Y squared.
So looking at just the numbers 8, 6, and 2, we are able to factor out the 2 from all of them. That's the greatest factor that we can pull out from them. What about x to the 4, x to the third, and x?
X.
Just x, right? And y squared, and y to the third, and y to the fourth?
Y.
Just y squared, yeah. So the GCF that we will be factoring out will be 2 x y squared, yeah. And if we do that, what are we going to get in these parentheses? 4.
X cubed.
Mm-hmm. And then the y to the 0, yeah, yeah. Plus 3.
X squared.
Mm-hmm. Y
Y
minus,
minus Y.
Y squared.
Y squared.
yeah, perfect. And that's it. The instructions ask us to factor out the GCF, and that's it. Just the GCF. In the exam, of course, we're not going to just factor out the GCF. We will examine the rest of the expression to see if there's anything else that we can factor it out. But let's do a little bit more. Factoring out by grouping. By grouping, we do this when you have 4 terms to factor it out, right? 4 terms. So imagine that you have these 4 terms, right? Factoring by grouping. Factoring by grouping. I'm going to start off with something simple. So imagine I ask you to factor it out, factor the expression. Say I want to factor it out. Let me put 5x plus 2 5x minus times x plus 2 minus 3 times x plus 2. Right. Say you have this expression. What can you factor out of these 2 terms?
X plus 2.
X plus 2. If you factored out the x plus 2 from here, you're going to have x plus 2 as the GCF, right? And you're going to be left with 5x minus 3. And if you understand this, then you will have no problems doing factoring by grouping. If you understand what happened between this line and this line, then that's basically what will happen at the end of factoring by grouping. That's the end. Usually that's if when student asks me a question about factoring by grouping is because they didn't get this step here. So here's an example for factoring by grouping. Factoring by grouping is done when you have 4 terms. 4 terms. And here is an example for something like this. So if I ask you to factor it out, the expression, say x to the third powered plus x squared plus 4x plus 4. Say we decide to group the first 2 and then the last 2, and so we create 2 groups. Here is the first group, and here is the second group. In the first group, x to the third power plus x to the second power. What will be the GCF for this one?
X squared.
X squared. So consider that we factored out x squared from that one, right? So x squared. And what are we going to be left in that parenthesis here?
X plus 1.
X plus 1. And in the second group, we can factor it out
4.
4. And imagine that we factored out positive 4, like this. What are we going to be left
Plus
with?
1.
X plus 1. And that's exactly what we had before. That what do you do next? You factor out anything that is common between these 2. So x plus 1 and x plus 1 is common in these 2 terms. What are you going to get when you do that? Say you factored out x plus 1. You're going to be left with x squared plus 4. And so this is how we're going to leave it now. We're going to leave our answer like this. They ask us to factor out the expression, and we had 4 terms, and when we have 4 terms, we're going to group them, right, into two groups, the first group and the second group, and we just group them out like this. Like that. And it could have been possible that they didn't give it to you in this order. They gave you x to the third power plus 4x plus x squared plus 4. So in your homework, you will see some cases where when you have 4 terms and you're asked to factor them out, sometimes maybe you will see that they're not matching up, and maybe you have to switch the order and make it work and so on. And here's another example, right? Another example. Factor the expression say x to the third power minus 2x squared minus 9x plus 18th. Say we have this one. Say we decide to group them out like this again, right? So x cubed minus 2x squared, and we have negative 9x plus 18th. What can be factored out from the first group?
X squared.
Yeah, so say we factored out x squared in the same group. We're going to have x minus 2. In the second group, what should be factored out?
9.
We should factor negative 9.
Negative 9.
Yeah, so if we factored out the negative 9th, what are we going to be left with in here?
X minus 2.
Minus 2.
Yeah, just x minus 2, and that matches up with the... So had you factored out the positive 9th, we would have left the negative x plus 2, and then you notice that you would have need to factor out the extra negative. So what does this factor into? X minus 2 times x squared minus 9th. Now consider this one right here, x squared minus 9th. Do you guys know that you can factor that one a little bit more?
Yeah. X minus
Because this one is nothing more than the difference of two
squared.
squares. This one is x minus 2 times x squared minus 3 squared. And the difference of two squares, according to what we had in the special formulas here, right? This is number 3 right here. If we had the difference of two squares, in this case x squared minus
Yeah.
3 squared, x squared minus 9, these will become a plus b. In our case, it will become x plus 3 and x minus 3. So that's what we're going to talk just a little bit about it now. So this one will just be x minus 2 times x plus 3.
And x minus 3.
And these will be our answer here. This will be our answer. So let's focus a little bit about that. Factoring by this, the difference of two squares, right? Yeah, so factoring out two terms, right? Factoring using the difference of two squares. This is for two terms. Like this. So here's an example for something like that, right? How do you factor out x squared minus 16th? This will be x squared minus
X minus
4 squared, so it will be x plus 4 times
x minus
x minus 4. Yeah, perfect. And there's nothing else you can do after that. What if you had this? So here's the next example. What if you had x to the 4th minus 1? What is this guy going to be? Well, this guy is x squared, right? X squared minus 1 squared. So these will become x squared plus 1 times x squared minus 1. Which one of the two can you factor it out, the left or the right? The x squared plus 1 or the x squared minus 1?
Minus 1.
The minus, these are the difference of two squares again. So we should attempt to factor that out a little bit more. So these will become x squared plus 1 times
x plus 1 and x minus 1.
and these will be the factor form of that one, this one. Yeah. Before we had that as the answer. Here's another example. Yeah, another example. How would you factor it out? X squared minus 4y squared. X squared minus 4y squared.
Same. There's x minus 2y and x plus 2y.
Yeah, so this guy here is x squared minus 2y squared, like that, right? So you can see that is the difference of two squares. So this will become x plus 2y times x minus 2y, like that. Hopefully that makes sense, right? And here's another one, right? Another example. What would you do? And this is a tricky example, so hopefully you catch it then. Yeah. So what would you do if you had 4x squared minus 36 y squared?
2x minus 6y.
Uh-huh.
2x
So,
6y.
so you can write it as 2x squared minus 6y squared like this, right? So these will become 2x plus 6y times 2x minus 6y. Is that correct? And the answer is no.
No.
That's not correct. There's something that we have to consider before doing all of this. And that goes back to what I said before.
Simplified before, right?
Before, we should,
By
Should have factored out the 4.
the GCF.
Yeah.
Yeah, so that will be ideal. Is the first thing that we have to think of. If there is any common factor that we can pull out, we should factor out the GCF. So giving this as the answer is not correct. This is not right. We need to factor it out 4 out of the expression first. So what is this going to be?
X squared minus 9.
9y squared. And now we should focus on that, right? So this will be 4x squared minus 3y squared, like this. So it will be 4. The 4, nothing happens to the 4 after you factor it out, it's still there. So you're going to have x plus 3y times x minus 3y, and this is fine. And is it possible to factor the sum of two squares?
Yeah, but not using that formula.
There was no formula for the sum of two squares. The sum of two squares will be a squared plus b squared,
Yeah.
for example. Is there a mathematician named Sophia Germani? She focused on answering that cleverly. It will depend. If it's 2-degree polynomial, then you can't do it. But if it's a 4-degree polynomial, it turns out that you can. So for our purposes, we are not going to consider anything higher than 3 degrees. Otherwise, we can factor out the GCF first, and whatever is left should not be bigger than the third degree. So just keep that in mind, that it is possible, but not for second degree or third degree. It's possible for 4th degree and so on, right? So when someone says, can you factor it out the sum of two squares, we will say if the degree is 4 or bigger, it is possible to do it. Yeah. Uh-huh.
Why did you turn negative 9y squared to 3y squared?
Yeah. So that this becomes the difference of two squares. This is a squared term, like a squared expression, and this is a squared expression as well.
But wasn't it already squared before?
Yeah. So the 9, I want to see this as something squared, right? So 9 is nothing more than 3 squared. Right, so if I put this together, it will be 3y, all of it squared, because that will give me back 9y squared. But this is a squared minus b squared. But going back to the special formulas, right? A here is x and b here is 3y. So it will be a plus b, so x plus 3y, and a minus b. So you can relate that. But if you can go from here to here, that's perfect. You don't have to go to the middle. The middle is just helping you to identify what a and b are from the special products. Right? What about this? Yeah, there we go. This will be a plus b times a squared minus ab plus b squared. Let me just give you 2 examples for that, right? So that to see how it will go. The first example, say we have x to the 3rd powered minus 1, x cubed minus 1. This one here is nothing more than x cubed minus 1 cube. 1 cube is 1. So we can see that this will be the difference of 2 cubes. And you can identify what a and b are going to be here. So this is going to be x minus 1, a minus b. And this will be a squared, so it's x squared, plus ab, which is x times 1, which is just x. Yeah, plus 1. It turns out that these later on plays a really important things. We call that in mathematics the roots of unity. And the roots of unity will be factoring out x to the n power minus 1 is nothing more than x minus 1 times x to the n minus 1, x to the n minus 2, plus x to the n minus 2, plus x to the n minus 3, and so on and so on. These always like adding them up. So if you divide by this, you get a formula for what x squared plus x plus 1 is from it. But it's not, it's just a fancy thing. So what about this one right here? Another example. Say you have x cubed plus 8, like this one. You can write this as x cubed plus 2 cubed, because 8 is 2 to the third power, right? So what is this going to be? Yeah, x plus 2 times x squared minus 2x, yeah, plus, yeah, 2, which is 4. There we go. And again, you don't have to worry about factoring out the second degree polynomial that you have there is not factorable. That's what I said up there. This is not factorable. Not factorable. Not factorable. Those things are not factorable. And now what we're going to do is we're going to talk a little bit about the factoring the 3 terms, right? Trinomials, right? And this is where you spend most of your time in high school trying to factor it out 3 terms. And so now that we develop these techniques of the 2 terms and the 4 terms, now the 3 terms should be easier because that we will apply a technique. Factoring 3 terms, trinomials. 3 terms. What we're going to do here is we're going to apply a method, and you probably heard of this with the AC method, right? That's some people call it the MP method for master product, but let's call it the AC method for just regularity. So the AC method. Have you guys heard of it, the AC method? Yeah. So, but now what we're going to do is we're going to combine the grouping with what we're going to do now. Here's an example for something like this, and we want to know whether sometimes something is possible to factor or is not possible to factor, right? And hopefully this method will tell us when something is not factorable and when something is factorable. And so consider this. Here's our first example. And our first example is simple. So x squared plus 7x plus 12, for example. It's supposed to be a little bit simple. How do we factor it out x squared plus 7x plus 12?
3 and a 4.
3 and a 4. But let's see how this will work with the AC method. So the AC, it stands for the first term and the last term, right? The coefficients for this one here will be 1, and so the A value here, the value for A will be 1, positive 1, and the value for C will be positive. So when you multiply them out, you are going to get positive 12. And what we do here with positive 12 is we're going to take a look at all the products of 12. So what are the factors of 12? So 12 would be 1 times 12, 2 times 6, 3 times 4. So all the possible pairs that multiply to 12, positive 12. So it's 1, 12, 2, 6, 3, 4, and the next one will be 4, 3, but that's there already. So we just want the pairs. We don't want to overuse things. So which of these will be the pair that we're going to select? Is the pair that adds up or subtracts to? Yeah, the middle guy, the B value, right? So in this case, the value of B is 7. And you can try 1 and 12. When you add them up, subtract them, you can make 7 out of that. 2 and 6, you can make 7 out of that. And 3 and 4, that fits perfectly because you can just simply add them up. So we will select these guys right here, this one. And if you ask me, do you select them as positive or negatives? You select them as positive because you want them to add up to positive 7th. And here's the trick. When the leading coefficient here, when the value of A here is equal to 1, then you're done because these are already the factors that you're going to use. When A is equal to 1, right? when A equals 1, this is enough. Because x squared plus 7x plus 12 will factor it out into x plus 3 and x plus 4. And the 3 and the 4 came from the pair that we selected, right? 3 and the 4 came from this pair right here. That pair. When it's not equal to 1, that's when we have to use a little bit slightly different approach, and that will be by grouping. Let's do an example for something like that. When we have when we have a leading coefficient other than So let's take a look at this example here. So I want to factor it out, this expression, 6x squared plus 7x minus 5. I want to factor this out. So what is the value for AAC here?
Negative 30.
Yeah, negative 30. And the pairs for 30, I'm going to go through all of them, but we will select which one works out, right? So 1, 30, 2, 15, 3, 10. 4 times what gives you 30? It doesn't work, right? So 5.
6.
Yeah, 5 and 6, and you stop there because the next one will be 6 and 5, but you already have that pair, and you stop there. And which of these pairs are you going to select? The one that adds up or subtracts 2?
3 and 10.
To 7, right? So 1 and 30 is not selected, 2 and 15 is not, 3 and 10 works because 10 minus 3 works, right? And this one doesn't work, so 3 and 10 will work. So we'll choose to select 3 and 10. How can we make this work so that the product of these two numbers here is negative and they add up to 7?
Negative 3 and positive 10.
Yeah. 10 minus 3. So 10 is positive, right? And 3 is negative. And now, because A here is not equal to 1, you see? If A here was equal to 1, we will be done, and those will be the factors. But if it's not equal to 1, what we'll do is we're going to rewrite the middle term into 3 and 10. Negative 3 and 10. We're going to select exactly the same variable as the middle, x. So how we're going to make that up? Negative 3x and
Negative
10x. Yeah? So it will look like this. 6x squared. And all of a sudden we're going to have negative 3x plus 10x minus 5. And you see that this is another way to rewrite 7x. You can't just choose how to rewrite 7x. It has to come from this pair right here. How do you factor that expression now? Because you have 4 terms.
You can do greatest common factor, take the 3x out.
Well, we're gonna pair them up like
first in the group.
grouping, yeah. So because you have 4 terms, what we'll do here is we're gonna group the first 2, and then the last 2 here. So in the first group, what can be factored out in the first group?
3x.
3x, and if we do the factor 3x out, we're gonna be left with. And in the second group, we can factor it out 5, positive 5, and if we factor out positive 5 from that, we'll get. Yeah, so 2x minus 1 is the common in both terms. So we're gonna have 2x minus 1 times.
3x.
Yeah, or if you want to write 3x plus 5 first and then times 2x, that's perfectly fine. The order in which you write the factors is not important. So these will be our answer for that one. But hopefully you get an idea of what we did here. What about when something is not factorable?
You leave it.
Well, you can't. So in the homework you will see factor completely, and you will see if possible. Because what if it's not possible, right? But let's give an example where something might not be possible to factor it out, right? So here's an example. Here's an example for something like that. Say I ask you to factor x squared plus x plus 2. Factor x squared plus x plus 2. And again, I'm going to say if possible. X squared plus x plus 2. So it has 3 terms. So we will take a look at the product of AC, right? What is AC equal to here? 2? Yeah. And what are the factors of 2? Just 1 and 2. So can these, is there any way that these can add up or subtract to 1? Yeah. So these will work, right? So let's try to see. So how will this work? If 2 is positive and 1 is negative. But then there's no way that the product is going to be positive 2. There is no way. So the pairs, right? 1 and 2. There is no way, right? No way that their product is positive 2 and their sum is 1, right? There is no way that that can happen, right? So what do we say with this expression? That this expression is
Not factor.
not factorable. So does x squared plus x plus 2 is not factorable, yeah. When we say not factorable, we mean, by the way, we don't mean we mean it's not factorable so that between the product of two polynomials, right? In the real numbers, it is possible to factor them out in the complex using complex numbers. So again, when we say not factorable, we really mean in the real, using real numbers, yeah. And in mathematics, if you are interested on when things are possible and when not possible, we have a branch of mathematics called Galois theory. Galois theory focuses on polynomials and when studies of polynomial behaviors of polynomials, factor polynomials, and it gets a little chaotic. In mathematics, you get a lot of corollaries and a lot of prepositions, a lot of theorems, and what you do with them is lemmas, for example, and you study them, and there is no way that you can give an example. There's no examples. It's all theory behind all of this. It's all just those variables, and so it gets a little boring when you do something like that. But it's for some people it's interesting, right? And you don't get to like you don't need anything else except for pen and paper for mathematics. Is inexpensive sometimes. So let's take a look at another thing, right? Here's another example, but this is factor the expression. Suppose that I give you something like this: 3 times 2x minus 1. Yeah, sure. Times 2x minus 1 times x plus 3 to the 1/2 plus 2x minus 1. Yeah, let's put to the second power and these to the third power. Times x plus 3 to the negative 1/2, like this. Say we have something like this, right? Just to get to the point of this. So in here you have a coefficient of 3. In here you have a coefficient of 1. So there is no way that you can factor out the 3 from that expression. 2x minus 1 has a power of 2 here. 2x minus 1 has a power of 3 there. You can factor 2x minus 1 to the lowest power. In this case will be 2. So far we know that we can factor out 2x minus 1 to the second power. What about x plus 3 here to the 1/2 and x plus 3 here to the negative 1/2? The lowest power, again, we will be factoring out x plus 3 to the negative 1/2. So what we are going to be factoring out here will be 2x minus 1 to the second power times x plus 3 to the negative 1/2. What are we going to be left with in here? So the 3 will stay there, right? The 3 will be there. What about 2x minus 1? It will be gone, right? Because you factor all of them. So you have x plus 3 to the what power now?
To the first power.
To the first power. Well, and the answer will be to the first power, right? So you have a 3 there. X plus 3 to the first power. Why will that work? Because what will happen when you multiply this with this? You add the exponents, right?
Yeah.
And negative 1/2 plus 1 will give you positive 1/2. So that will work out. If you're not sure how to get these ones, what you do is you have this expression divided by this. So you have this over here divided by this. You see these will cancel up. The 3 will stay there. And this divided by that, you put this up and you end up adding the exponents there as well. So again, I can say a little bit more about that, but it will be 3, x plus 3 to the 1 power. What about the next one over
I
here?
get one thing. Why did you put x plus 3 to the power of 1 power?
The power, so that it is clear that there will be a power of 1. Next, I'm going to simplify this. And now I'm not going to put the power of 1 because it's not, we don't do that. But do you know why the exponent is 1?
No, that's what I'm asking.
Yeah.
Why is it 1?
So do you agree with me that if you multiply this with this, what are you going to get? X plus 3 to the what power?
So what do you mean if I multiply this with?
X plus 3 to the negative 1/2 times x plus 3 to the power of 1. This will give you x plus 3 to the power.
If I multiply, I will get different result.
What would you get?
I don't know. I have to do that
You can
calculation.
also like divide, right?
Yeah, so that's what I'm saying. Another way to think about this, how we get this, is you divide this term by this GCF.
So you can get 1/2 minus 1.
So I'm going to write it like this, and let me know if this makes sense to you here. So this part right here, the way that we get this is 3, 2x minus 1 squared, x plus 3 to the 1/2, divided by what we factored out, which is 2x minus 1 squared times x plus 3 to the negative 1/2. So do you see that these will cancel out the 2x minus 1 to the second power, right? So the 3 will be there. You see it here, you see it here. And what is this going to simplify to, this one right here? What is that going to simplify to?
X plus 3.
We're going to move the negative exponent
Uh,
up.
you
So,
add 'em.
and then we add, so we're going to have 3, x plus 3 to the 1/2 times x plus 3 to the 1/2. And now we add the exponent, so we get 3, x plus 3 to the 1/2 plus 1/2, right? But hopefully that makes sense, that how we get 3, right? X plus 3 to the...
But at the denominator you put 2x plus, at the denominator you put 2x minus 1 to the power of square.
Yeah, that cancels off with this one.
No, but it says cube right here. It says 2x minus 1 to the
Yes,
power
they
of
can-
No, I haven't done this yet. I still need to write more over here.
So you're doing the left part.
Yeah, the left part.
Then why did you put 2x minus 1 square?
Because that's what's here.
Then what happened to the 3?
The 3 still stayed there. And you have to write the entire thing.
So you multiply you divided the entire thing by 2x minus 1 and then x plus 1.
Yeah, this one.
I see.
So let me finish this up so you can see
Are you
the ending
getting
of
why
this.
this method is different from the other method that you just did?
It's the same thing. It's just an extension of what we did before. But let's just finish up, right? And then I can answer your question afterwards if you want. So what about the rest over here? It will be plus.
2x minus 1.
Yeah, so 2x minus 1 to the power of 1, right? Because we factored 2 of them out. And you don't have to write the 1, but I just do it for emphasis. And then the x plus 3 to the power of negative 1/2. Nothing, because you already factored the entire thing out. Now, the last thing that you have to worry about is, because the exponents here are 1, you should simplify them out. So it will look like this. 2x minus 1 squared, x plus 3 to the negative 1/2. And in here, you're going to have 3x plus 9th plus 2x minus 1. Because that exponent of 1 is not enough to protect anything. It's just going to allow things to distribute. So we're going to have 2x minus 1 squared times, notice that the exponent for x plus 3 is negative, so I'm going to move it on the bottom as x plus 3 to the positive 1/2, like that. And what are we going to have in those brackets in there?
5x.
Uh-huh.
plus 8.
Yeah, 5x plus 8. So these will be the expression. On the bottom, you have a choice to write this as the square root of x plus 3. But you shouldn't leave it up here as a power of negative 1/2. The negative exponents, again, you want to convert them into positive exponents. That's the end of today. I will see you guys tomorrow on Thursday. We don't meet up on Thursday because it's a holiday, right? And if you have any questions, we can stay here a few minutes to answer them, right? Yeah.